So let's continue talking about finding the volume of rectangular prisms. And first of all, taking a look at this rectangular prism, notice that each of the dimensions, the height, the length, and the width, these are all the same. These are all 4 centimeters. So this is a specific type of rectangular prism. This is what we call a cube, since all the side lengths are the same. And remember, when dealing with the volume of rectangular prisms, we're asking how much space, how much three-dimensional space can fit inside of an object. So you can imagine, you can reframe the question, how much liquid could we put inside of this box so that it completely fills it up? That's one way to think about volume, is how much of a substance you can actually put inside of it. So with volume though, remember that we're essentially asking how many unit cubes we can fit inside of the prism. Where a unit cube, remember, is just a cube where each side length, each dimension is one. So its height, its width, and its length are all one unit. In this case, we'll be dealing with centimeters. And the volume of this unit cube, we would say, is just 1 cubic unit. So how many of these can fit inside of our rectangular prism or inside of this bigger cube? And there were two different approaches. One, and this is essentially the starting point, is that we can split this shape up into a bunch of unit cubes. And once we did that in our previous video and our introduction on this topic, we notice a pattern that essentially, to find the volume, you can use a formula where the volume of any rectangular prism is equal to the height multiplied by the length multiplied by the width. So this is the formula we found, but this formula just comes from splitting up this bigger shape into a bunch of unit cubes. So let's do that first. Let's look at what happens when you actually split this up, and then we can actually just count it out and compare it to this formula to make sure that this does in fact make sense. So to split this up into unit cubes, we're going to take each of our side lengths, each of these dimensions, and split them into length 1. So for instance, for this side length here, we're going to split it into 4 different pieces. So let me actually use my line tool for this, where now notice that each of these has length 1, or 1 centimeter. And we'll do the same thing for the height, since notice the height is 4, so this length and this length are also 4. So we will be splitting this up into 4 pieces as well. And this won't be drawn perfectly, but you can get a general idea. And now we're going to do the same thing for the top and the side, and we'll be able to see the unit cubes after that. So let me split these up into essentially 16 boxes here and 16 here, and then from there we'll be able to see all the unit cubes. So now that we have all of our essentially faces split up into 4 by 4 arrays, what we can notice is that now we have a bunch of unit cubes and we can count them up. Since again, each of these side lengths is length 1. So notice for maybe this top front right corner that this is a unit cube. It has height 1, width 1, and length 1. So this is 1 unit cube and it has a volume of 1 cubic unit. And all of the ones around it, these are also unit cubes. So at this point, we can just count them up. So notice we have 1, 2, 3, 4 in this top front row. And we also have 4 rows of that. So now we're really just concerned with this top piece here of unit cubes. And so we have 4 in the front and we have 4 rows of that. So you can count that there are 16 if you just actually count them out. That's 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 up top. And then notice you have 1, 2, 3, 4 rows of that. So you have 4 rows of these 16. You have 16 here, 16 more there, 16 more here, and 16 on the bottom. And we know that 4 times 16 is just 64. So in total, there are 64 unit cubes here. So our volume, which usually we can just call V, but our volume is 64 of these unit cubes, and their units are cubic centimeters. Now, this process is fairly tedious. It takes a while to draw these out, and then you have to count them up. And this is only for side lengths of 4, but if you had something like a side length of 35 or 112, this would take a very long time. So this is not an efficient process, but this process allows us to notice the pattern. Since notice that 64 is really just the product of 4 times 4 times 4. So if we take each of our dimensions, our height, our length, and our width, and if we multiply them together, we get this 64. So it does make sense that this is the formula. This formula that we notice on the previous problem from the intro video. And for cubes, they have a very specific formula. Since all of the side lengths are the same, these are always the same value. So we can generalize this further and say that for the volume of a cube, that we're just going to take a side length and multiply it by itself 3 times. And multiplying something by itself 3 times is the same thing as cubing it or raising it to the 3rd power. So the volume of a cube is one of the side lengths raised to the 3rd power. So this is a formula we can use when we see a cube. So if they had, let's say, 10 centimeter side lengths, then we can just put 10 for our side length, raise it to the 3rd power, and the volume of that cube would be 1,000 cubic units.